Okay, so welcome back to another video. So in today's video we have the following infinite sum of 1 divided by the swinging factorial of n. And I should write that the definition of what n, the swinging factorial of n is, it's defined as, so I have this symbol over here, we said that that's equal to n factorial and then divided by the floor of n divided by 2 factorial square. I can't really exactly find the application specifically used for this. This is actually known as the swinging constant, but I would assume that the number, the sum itself will be used in form of in combinatorics, since we have the floor function over here, since you see that a whole lot. But so if you see any sort of, if you find any applications specifically of what this sum is used for, then feel free to comment down below. In other words, this is actually can be also described as the swinging E. The way it's described that way in a sense where if you write E and expand that in the form of the Maclaurin series, Taylor series, Maclaurin series, it's defined as the infinite sum from, of course, starting with your index n equals 0 of 1 divided by n factorial. So the swinging E is just basically, you just replace that factorial symbol with the, we'll call this the vertical tilde symbol. And then now basically, now the way to tackle on how to evaluate this infinite sum is basically just rewrite the sum in a way that we can actually use the definitions. Specifically, eventually, as we move forward, we're going to use different definitions of the beta function and in relation with the gamma function as well. Then expand that out some more. There's actually going to be, you're going to also see that the geometric series is also used as well. And then eventually we'll come across with calculating the definite integral to the point where we can actually find the closed form of this infinite sum. So anyway, with that, let's actually just jump straight in. Forgot to say that this definition for the definition for the swinging factorial is actually, this is for all the natural numbers. All right, let's actually start. So we're just going to call what's actually called what we're given capital S, right? And we have 1 divided by the swinging factorial of n. So we'll just flip the reciprocal so that we have the infinite sum. So from n is equal to 0 of the floor of n divided by 2 factorial square and then divided by n factorial. Now we could expand this out if we want to, but that's not really going to do you justice. You're just seeing how the representation expands out. We're going to take the creative approach and actually we're going to split this into 2 sums, to where one sum will take into account for our index for the even terms, and then add that with the same thing but taking into account to the odd terms. So with that, let's actually write this. I'm actually going to call this index. I'll just write that as n even and then n odd. And so this is just the same thing written over here. So we have the floor of n divided by 2 factorial squared divided by n factorial. Okay, and then we add this with our sum again, that we're taking this to account of odd terms. And we have the floor of n divided by 2 factorial square and n divided by n factorial. So let's actually, now we can actually define, let's actually call our variables for these floor functions over here. All right, so focusing on this floor function over here of n over 2, since we're taking into account of even terms, so that actually says that the floor of n divided by 2 is equal to just n divided by 2 for even terms. And then for over here, for the odd terms, so n divided by 2 is equal to n divided by 2, and then subtract that when 1/2 for odd terms. Now we have the way we describe how those floor functions are, specifically with how the association of the index. So now let's actually just call some variable and define how we define these functions. So now let's say that suppose we let m equals n over 2, and then now we'll also let another variable, we'll call this k. We'll let this take into account for the odd terms, so we'll let that be k is equal to n divided by 2 and then subtract with 1/2. Okay, so now let's actually substitute this stuff back together. We'll focus on each of the sums one by one for even and odd, so we'll get to that eventually. So focusing on the even, so we have that for the even, if we have n is even, and then if I just substitute our floor for what we said was n divided by 2, so this is just n divided by 2 factorial square and then divided by n factorial. If we write this out, we say that this is just, okay, that's just going to be m factorial and then square. But since we're doing with the infinite sum again, so I could just put back the our original index, but we just put this for m is equal to 0 to infinity of m factorial and then square, and then the denominator n squared. So if we solve for n and then just replace that back in, where is it, right over here, so then this will just be 2m factorial. What I can do from here is we're going to manipulate some things eventually, so why don't we actually do this. So how about this, I add we multiply with a number that's like its predecessor. So the way like we have specifically for 2m, the predecessor to that would be 2m plus 1, and then you subtract 1. That's how factorial is defined. So if I change this to 2m plus 1 and then factorial, then that means that would have to be the case that 2m plus 1 has to be multiplied to the numerator, since it would make sense so that it cancels that term out just to be left with what was originally written. M is equal to 0. Then we have 2m plus 1, then m factorial square, and then we just divide this by 2m plus 1 factorial. Okay, and now let's actually now substitute everything back for the odd terms. So n odd, n divided by 2 factorial square, or excuse me, this is actually supposed to be minus 1/2, forgot that part. So subtract 1/2, then factorial squared, then divide that by, okay, so we have to solve for n over here, or actually not yet, that will come later, so actually I have to just put back the n factorial. Okay, and now the next step over here, now just change this back to the infinite sum, so this time we have the index is k is equal to 0. Then over here, and we set that this was k over here, so that means this would just be k factorial square, and then divided by, so we have n, let's see, if we solve for n, so let's see, I had a 1/2 over here, then multiply by 2, so then that would have to be the denominator, would just have to be 2k plus 1 factorial. So we now we actually have both the n and the n is even and odd expanded out and then rewritten in terms of what we have for the substitution. So now we can actually go back to here and then write this as our new sum. So I'm basically just taking the sums of these two. So that means we have the infinite sum, m is equal to 0, 2m plus 1, then multiplied by m factorial squared divided by 2m plus 1 factorial, and then add this with this sum over here, factorial, k is equal 0, then k factorial squared, and then divided by 2k plus 1 factorial. What's nice here is the indexes does not matter in this case. What I'm really getting at is that what we can do is we can actually combine this under one sum. But if you were to write out the expanded series, you know, the variables doesn't matter just as long as they share, specifically because they share the same denominator too, disregarding how the index is written. Because if you were to expand this out, they share the same denominator. So really, what I can do from here is we can actually just combine this under one sum. There's a k factorial square, then k factorial square here. How about this? Let me actually just combine this under one sum, and then we can discuss a little further what's next. So it's just a dummy variable over here, so I'll just put this back I'll put this as an m, then our index m. So we have, let's see, 2m plus 1, then multiply m factorial square, add this with m factorial square. That's just coming from here, just place an m over here, and then we just divide this by 2k plus 1 factorial. So you see that if we actually you can see that I can actually just factor out an m factorial square to both, and so we have 2m plus 1 and then plus 1. So meaning I could just add that plus 1 back into this quantity, so this become a 2m plus 2. So now we have, so m is equal to 0, and then this will be 2m plus 2 multiplied by m factorial square, and then divided by 2m plus 1 factorial. And then next, I'll just factor out 2 from over here. So this is just double the quantity, m is equal to 0. Then on the top, this will just be m plus 1, then multiplied by m factorial square, and then divided by 2m plus 1 factorial, like so. So next, what I want to do is we're actually going to use a couple of formulas, specifically the functions, really, specifically the gamma function and the beta function. Let me see if I got room in the bottom. So we're gonna actually define the following functions over here. So see, the first one we have is specifically for gamma, and that says that gamma of n plus 1 is actually just equal to n factorial. And then the second formula, this is going to be in terms of beta, and that says that beta, we're just call this capital B, and for example, we'll say some variable x, y. That's actually going to equal to, in terms of gamma, gamma x times gamma y, and then that's divided by gamma of x plus y. And then the last one, I think I'm going to write this over here, and this is again for beta, another form of beta, but this is in terms of a integral representation that's going to be equal to the integral from 0 to 1 of t to the power x minus 1, then multiplied by 1 minus t, and then y minus to the power 1 minus 1 dt. Okay, so we have these formulas over here. So basically, this is just, we're going to rewrite what we've shown so far for this expression over here, using in terms of our beta and gamma. Starting from here, now the way I can rewrite this is m factorial square. We can actually use the definition of beta and just replace that in there. So let's see, we have, so in this case, this will be 2 times our infinite sum is equals 0 of m plus 1, then multiply with, so we have m factorial, so this will be gamma of m plus 1, then you do it again a second time, m plus 1, since it's square, so write that out. And then at the bottom, let's see, so we have 2m plus 1, just use this in terms of our gamma, so we had a 1, so this will, in the denominator will just be gamma of 2m plus 2. And you see, we have gamma n plus 1, then gamma n plus 1, and then gamma 2m plus 2m plus 2. We can just use that definition in terms of gamma to write our beta function over here. So we have 2, and then multiply with our infinite sum. This is just n plus 1, then multiply with the beta, capital B, of n plus 1, comma, n plus 1. Now we just replace what we have, beta n plus 1, and use this formula over here to write this in terms of our indefinite, or non-definite, definite integral. So next, 2, then write the same thing again, then replace our beta function in terms of the integral representation over here. We solve for x, and then we solve for y. Well, not really solve, we just plug our x and y input back into here to get what the exponent is. And so by doing this, 0, 1, this will be t to the power m, then multiply with m plus 1, or not m plus, excuse me, so this will be 1 minus t, and then to the power m, then dt. Okay, and now I can actually just interchange so that I move the sum into the inside the integral. Simply, this is uniform convergent. So then now we have 2, or actually, my bad, that's supposed to be the integral over here. So this is 2 times the integral 0, 1. Now the sum, m equals 0 of m plus 1, then 2, then t to the power m, then 1 minus t, m dt. Now I'm going to actually use a little fact over here, and this is in terms of the geometric series. And what that says is that specifically for our absolute value, for example, we call this r, that's less than 1, then we say that the infinite sum of m plus 1 and then multiply with r to the power m, that's just equal to 1 divided by 1 minus r squared. And I can actually prove this too. The way you do this simply is, if we just call this s, after I go to disprove, I'm gonna erase all this, so just to save some space to make room for the work. So what you do is, if you were to expand the series out, so specifically for the left hand side, we get 1 and then r times 0, then plus 2 r times 1, then plus 3 r squared dot dot dot. Okay. So let's say I multiply r to s, so this means I'll have r, then plus 2r squared, then plus 3r cubed, then dot dot dot. Now if I take the subtraction of both sides, so it's f s minus r times s, then everything from each of the quantities starting from 2r will decrease by 1 and so forth. So we have 1, then plus r, then plus r squared, then plus r cubed, I should write it like plus and then the 3 dots. That's equal to, well, we know this simply because if we use the definition of the geometric series with our, common ratio being 1, that's basically just 1 divided by 1 minus r. So if I factor out s, so s and then r minus 1, then 1 divided by 1 minus r, then I divide both sides by, it's actually supposed to be a 1, then minus r, then divide that by both sides, we get that this is just 1 minus r, 1 minus r, and then quantity square. Proof complete. So we can use this to rewrite this in terms of our, just to get rid of our summation symbol. Okay, so that's good. Get rid of the proof. So if we use our fact that the summation over here, we can write this as 1 divided by 1 minus r square. Specifically, I'll put this over here. We'll say infinite sum m is equals 0 of m plus 1 t to the power m and then 1 minus t to the power m. We just use that definition and say that, well, specifically, let me write this on the one line below. We say that because they share the same exponents, I could just distribute the t onto the quantity expression inside. Infinity m equals 0, m plus 1, and then this is just t, just distribute the t into here, so t and then minus t square, then to the power m, and so that's just equal to 1 divided by, so it's just substitute with the r and this quantity over here, so then that'll just be 1 minus t and then plus t square and then square again. So we have that, so now we can actually just replace our summation with this expression over here that from the geometric series. So this now becomes 2 times the integral from 0 to 1 of 1 divided by 1 minus t plus t square, quantity square dt. How to integrate this? Well, we can actually, what we can do for the denominator specifically, that quantity expression inside, is we can actually complete the square, and this is very easy to show, so I'm just gonna skip that step. But once you actually do this, the completing the square, you're gonna get that for the new denominator. This is going to be, let's see, so this is 1 over here. Then we have t, subtract with 1/2 square, then add this with 3/4 square dt. We have our new rewritten integral. So now the last thing is just calculate this definite integral. So how can we do this? Let's actually perform a u-substitution. Let me actually write this in a new marker. So we're going to perform a u-substitution. So let's say we call this, well, specifically, I'll let t minus 1/2. We're going to let this equal to the square root of 3 divided by 2, and then times tangent x. So now we do the differentiation. So dt is equal to, so it's just a square root of 3 divided by 2. Then the derivative of tangent x is just secant square x. So now we just have to rewrite our, now we just have to put in the substitutions together. So when we do this, let's see, so we have our old integral over here. We'll just write everything into the new. So we'll start off with the old and then convert it to the new. So we have the new integral. Let's see, divide the square root of 3 divided by 2 both sides. That 2 will cancel. So outside, this is just going to be a square root of 3. And then we have to calculate our new bounds. So let's see, if we plug 1 for t, 1 minus 1/2, that's positive 1/2. Then multiply the 2, so okay, so you just, it'll be 1 divided by square root of 3, then square root of 3 divided by 3, inverse tangent of that, so that means this is just pi over 6. And then the bottom is the same thing, just do it again, but it's in terms of negatives, so actually this is just going to be negative pi divided by 6. All right, and then the top will be a secant square x, and then we substitute everything in on the bottom. So let's see, t minus 1/2, we set that square root of, so over here that'd be the square root of 3 divided by 2, tangent x square, okay, and then add this with 3 divided by 4 square dx. And what's neat is what I can do is All right. So if we can write this out in full if we want to, but I'm actually just gonna skip the steps and I'll explain this to you. So what I can do is, so let's see, if I square the inside this quantity, so this will be 3 over 4 tangent square x plus 3 over 4. Factor out 3 over 4 for both of these terms. So we have 3 over 4 times tangent square x plus plus 1, that's quantity. Square that again over here, so we have, 9 divided by 16. Then I can actually factor out that 9 over 16, then divide by here. So now that the constant outside will be 16 squared 3 divided by 9. Then we have our integral pi over 6, negative pi over 6. Let's see, secant square x is still on the top. So inside over here, this is tangent square x plus 1. You use your trig identities, that's also the same thing as secant square x. Square that again, so you get secant x, or the secant fourth of x, we'll say that. Okay, so secant square x divided by secant fourth x, so if you simplify that terms out, you'll get 1 over secant square x, then rewrite the terms again with the trig loss, that's actually just cosine square of x, then dx. Now, calculating this is simple. What you can do is use your trig formulas for writing cosine square of x as 1/2 and then plus 1/2 multiplied by cosine of 2x. So, and I'll factor out the 1/2 and put that outside. So let's see, so if I factor out the 1/2, yeah, if I factor out the 1/2, that would be 16 divided by 18, and then that'll just become 8 times square root of 3 divided by 9, negative pi divided by 6, pi divided by 6 of 1 plus cosine of 2x, then dx. Okay, and this is a very simple definite integral to compute. So when I do this, let's see, 8 square root of 3 divided by 9, and then over here we have x, because the antiderivative of 1 is x, and then you doing u sub over here, so this is just 1/2 and then sine of 2x. And then compute our bounds from pi over 6 to negative pi divided by 6. And computing these bounds is very simple. So over here, you're going to get that this is just 8 square root of 3, 9. Multiply this out. We're going to get that if you actually just solve this work, I'm just going to complete the step, which skip that step, which have pi divided by 3. And then we add this with the square root of 3 divided by 2. And now it just comes simplifying it out. So let's see, if we actually just do the, so we have 2 pi, and then add this with plus 3 times square root of 3. Well, actually, we don't do that exactly. You just distribute the 8. I'm just overthinking things a little bit, sorry about that. You can just distribute the 8 square root of 3 to 9 to pi over 3, and then the other one to square root of 3 divided by 2, and we're just gonna call that at the end of the day. So doing this, you're gonna get that the final answer. This is just 8 pi square root of 3, then divided by 27, then distribute the 8 square root of 3 over here. So let's see, 3 times 3, or well, square root of 3 times square root of 3 is 3, then 24 divided by 18, then we get that this is just plus 4 divided by 3. And there we have it, the final answer in red. And you know what's really neat about this? So we set that S, which was our given, our given over here, we just rewrote this in terms of using the definition of the factorial. So S is equal to this constant, the swinging constant. What's neat is that if you actually just solve this for pi on its own, we actually get a new form of pi, approximation of pi using in terms of the swinging factorial over here, which I think is very neat. So yeah, long computation, all the work over here. That's pretty cool if you ask me.